It's great to have Nate here. It's great to have Nate here. Nate is graduated last year with super IT in the efficient consensus and distributed systems. He's done great work in the field. I think one of the works he's going to talk about today. And now he's the CTO and co-founder of MegaLabs, which works on Mega. And on a more personal note, he was my mentor for 1.5 years at MIT, and he's been great. Thank you for being here.
Thanks a lot for the thanks a lot for the invite, and it's very nice to see friends in real life. So today's talk is about a kind of interesting primitive that I want to tell more people about. I think I found it very useful in many distributed and decentralized systems, and this primitive is called set reconciliation. So this primitive solves a basic problem in distributed system, which is synchronization. And synchronization is really a task that is everywhere in distributed systems. For example, you have rsync, which synchronizes two directories across computers. You have those gossip protocols that synchronizes, for example, memory pools in blockchain systems. Of course, you have this Bitcoin and Ethereum peer-to-peer network that synchronizes block states and block bodies. And there's a very nice abstraction of this whole primitive of synchronization, and it's called set reconciliation. And imagine that Alice and Bob each holds a set of items, and here each file that regarded as an item, and the items can be anything, right? For example, file system blocks, there's 4 KB file system blocks, database keys or entries, Bitcoin UTXOs, tweets, chat messages, DNS records, whatever, right? And the goal here is to compute the symmetric difference of their two sets, set A and set B. And in other words, they want to learn the items that are exclusive in only one of the two sets. And that is the definition of the symmetric difference, right? And by the way, interrupt anytime you have a question. Right, so the definition of the symmetric difference is basically the items that appear only once in either A or B. And they want to distributedly compute this stat so that they can learn the items missing from each other, right? So this is the end goal. And so there's a kind of a very basic lower bound on the computational cost of this task of synchronization, and it's coming from information theory, right? Because you ultimately want to learn the items that are missing, so you have to kind of communicate as many bits as the size of this symmetric difference in order to finish this task. And you can never do better than basically the size of the symmetric difference when you want to finish synchronization. It's the baseline of the communication cost. And of course, this task has been there for a long time. And there have been many straightforward solutions to this problem. And the most basic one could be that Alice, for example, on the left-hand side, just send the entire set to Bob. But of course, it's very inefficient because Alice basically sends kind of an amount of data that's on the order of the size of her set. But even if it's a kind of a trivial and a straightforward solution, we still use it a lot. For example, in Bitcoin, right? We just blast the entire block, and we even flood it across the peer-to-peer network, disregarding the fact that the receiving end might already have got so many of the transactions in their memory pools. There are some alternatives to sending the raw data. For example, you can hash the items, or you can compute a Bloom filter over the items. But on the other hand, these don't decrease the amortized cost of this solution, right? Because even Bloom filter is still linear to the size of the set. Yep, and the problem is severe if the sets are very large, and there's a significant overlap between them. So basically, you're communicating a lot of data in order to just communicate maybe one or two missing items to the other end. You're right, and a more optimized solution, which is adopted at least in Ethereum, is for the two parties to walk a hash tree together. And suppose that these two trees are the Merkle trees, and usually this talk is for a cryptography audience. So I spent some time explaining the Merkle tree, but basically you can just compare the two Merkle trees from the root, and if the roots are not the same, then you open the immediate children, and you can compare the children, and basically you walk the tree until you find the actual missing item, and until you find all the actually missing items. However, although at the end of the day you only communicate these missing items because you can pinpoint them, but walking the tree takes a logarithmic factor of communication, and also it takes a logarithmic number of steps, where kind of a logarithmic to the size of the set, not to the size of the difference. Yeah.
So this logarithmic is the number of files.
Correct, in the number of files.
Well, it'd be comparable with the size of the
That's a very good point. Usually it's the hashes are much smaller than the actual files. But yeah, in many settings, for example, transactions in Ethereum and UTXOs and say database entries, especially database keys, the files are actually very small, like 32 bytes or even shorter, which is actually comparable to the size of the hashes. It's a very good question. This is where this problem becomes interesting. Yeah.
Do you assume both parties are honest?
Correct. Good point. Yeah, because they are kind of doing this for the sake of themselves. So we assume it's an honest part. Both parties are honest. It's a very good question because there is actually a valid, I think, a very practical attack model where there's a third party, where basically a third party kind of can influence the content of their sets. And by maliciously injecting problematic items, maybe the third party can destroy this protocol, even if the two parties that are actually participating in the protocol are honest.
I mean, even you sort of alluded to a rationality behind doing this honestly, but wouldn't there be like incentives to hide certain transactions from here?
Yeah, that's a good point. So I actually talked about this primitive to a few MEV searchers, and a common problem they share with me is that they want to exchange their order flows. They probably buy those order flows from, say, MetaMask, those wallets, right? And it's valuable because if you have the order flow, you can front run the transactions more efficiently, more effectively. Yes, so there was actually a request that, hey, how can I make sure that when we exchange the order flow, the other end really pays for the novel transactions the other end learned from me? So actually there's a solution. I think I might not remember the actual detail, but I think the solution is that one party can commit to the set that the party currently holds. And notice that you want to commit to the entire set that you hold, because otherwise, if you commit to a smaller set, then after the protocol, you'll be charged more. And the protocol works like this. So Alice commits to her set, and then Bob sends Bob, and they participate in reconciliation. And then Alice will need to respond to Bob with the symmetric difference, such that Bob can apply to his own local set that will bring Bob's set to be the same as Alice's original set. So okay, so and Bob can check this fact by comparing the commitment of Alice's set that Alice sent prior with Bob's set after applying the diff. Right, and then Bob can accurately know what's the actual difference between Alice's committed version and his set. And now Bob can charge Alice based on based on the diff. And here, if Alice initially committed to a smaller set, then Alice will be charged more.
Interesting.
Yeah.
Interesting. Yeah, we can talk more.
Yeah, it's so basically I think the answer is that there's there's some kind of a plugin, or you can layer a protocol on top of this primitive. Yeah. Okay, so hash tree traversal still not optimal because of this logarithmic factor in latency, in number of steps, and in this metadata exchange. So there's actually a very promising solution. It's been there since I think 20 years ago, which is to use a data structure called a linear sketch. And a sketch is basically a summary of a set of items. And under some conditions, which I will talk about later, you can decode a sketch to, for example, you have say this is a sketch of A, is computed by some algorithm over the set of A. But under some conditions, which we'll talk about later, you can recover the items in the set of A through an operation called decode, right? And also a linear sketch has a very nice property that you can linearly combine two sketches. So suppose that you have a sketch of A and you have the sketch of B, then there's a linear operation that can be defined that allows you to kind of combine them. And the interesting result is that if you combine the two results, if you combine the two sketches, then the resulting sketch will be actually the sketch over A delta B, or the symmetric difference that we actually want to compute. So now the solution is quite straightforward. Alice computes her sketch and sends her sketch to Bob. And Bob will locally perform this linear combination and then perform a decode. And if we're fortunate, then Bob can recover the items in the symmetric difference, because you can recover items from the sketch, and then Bob can just distribute the items to him and to Alice. And now let's kind of dive a little bit deeper into how a sketch is constructed and how this decode or recovery operation is done. And a sketch is basically a collection of what we call symbols, right? And each symbol is a sum or the linear combination of a few items. And imagine that, so this is the symmetric difference that we want to recover. And this is the corresponding sketch. And recall that each symbol is the linear combination of a few items. And the way this linear combination is defined is that each item is randomly mapped to, say, k number of symbols. And here this bipartite graph shows the mapping between items and symbols. For example, A is mapped to symbols 0 and 4. And for example, the 0th symbol is the sum or the linear combination of items A and E, right? And so on and so forth.
Wait, but you have 7 symbols and 6 items, so it's larger than just sending hashes of the items, no?
Correct, but it's important to remember that here you only we're talking about the sketch after this linear combination. So it's correct that the sketch should have more symbols than the number of than the size of the symmetric difference, but it's not related to the size of original sets anymore. So this is the part that makes this algorithm independent of the size of original sets, but only dependent on the size of the symmetric difference.
Even like the construction you've just shown, it's like a Bloom filter, but instead of a counter, you say something else.
Yes, exactly. So there's a variant of Bloom filters called counting Bloom filters. And a counting Bloom filter supports an operation called subtraction. So basically, you can subtract 2 Bloom filters. The construction is very simple. In Bloom filters, you set the bits, right? But in a counting Bloom filter, you don't use a bit, you use a counter. And the moment anytime an item is mapped to a particular cell, you increase the counter instead of flagging a bit. And then you realize you can kind of subtract 2 Bloom filters, and the resulting Bloom filter would be the one for the symmetric difference. Yeah. So yeah, it's a very good question. And this is the way a sketch is constructed. And to decode a sketch, we use an algorithm called peeling. And it's this peeling algorithm comes from actually coding theory, and there is a class of codes, like error correcting codes, not program. There's a class of codes called LDPC, or low density parity check codes. And this is the class of codes that is being used in 5G communication, and it's exactly the same idea to decode the LDPC codes and such a sketch. And I'll show you how. So first, recall that you have this mapping between items and symbols, right? And I add some opacity to the items because they are not decoded. None of the items is decoded yet, right? So you only see the symbols at this point. And you start decoding by locating a symbol with only one item mapped to it. And the way you tell if a symbol has only one item mapped to it is by using a counter. And also remember that now in our structure, in our data structure, in a sketch, a symbol has both a counter, which allows you to tell if a symbol is has only one item mapped to it, and also the sum of the items mapped to it when you were constructing the sketch. So now you realize that symbol number 2 is the sum of one item that is mapped to it, which is D. So you can recover D already by just taking the sum out of in present in symbol number 2. And once you have the item D, you use the same algorithm. You use the same like random process that mapped these items to the symbols to realize that, hey, item number D is also mapped to symbol number 5. So you can subtract item number D, which you just recovered from symbol number 5, and symbol number 5 now becomes like a singleton or a pure symbol in coding theory.
You always need one extra symbol in the good case. It has to be 1, 2, 3, always. Because otherwise you couldn't fully decode everything.
Actually, I think if you just look at this relationship, look at this mapping as a linear system, right? The symbols are the linear combinations of items, and in the best case, you only need the same number of symbols as the items to solve for this linear system to have a unique solution.
Exactly the same.
Exactly the same. Yeah. Yeah, because it's like x plus y equal to 2 and x minus y equal to, say, 3, and you can already solve x and y, right? It's you only need that number of equations or symbols to solve it. But since it's a random process, in practice, usually the same number doesn't work, because the items are mapped randomly to the symbols, and I'll explain the exact condition under which you should construct this mapping in a bit. Okay, so now we realize how we can decode this. It's kind of a recursive, it's kind of an iterative process, right? You recover item F from symbol 5, and you can subtract F from the other symbols it is mapped to, and just repeat the process, and you can recover the entire. You can recover the entire thing. And there is some mathematical backing of this process that says, if you construct this mapping in a smart way, then the number of symbols you need is actually going to be linear with a very small coefficient, like 2 or 1.8, to the number of symbols. Sorry, to the number of items. Okay, so this looks very good, and it is not my work. It's done, I think, by Fox even back in 2003. So. But there's actually, so what's new here in this work, right? I think what's new here is that in like classical, in normal sketches, there's a small issue, which is they have fixed capacity, right? And the reason they have fixed capacity is that based on math, a sketch is only decodable if it has about twice as many symbols as the items that you want to recover, right? And this is because, again, the items are mapped randomly, so you might end up with this very unfortunate scenario where you don't even have a pure or singleton symbol to start with, right? In this particular case, so you cannot decode it. Or maybe you have a few singleton a few singletons at the beginning, but you run out of singletons during the process. So you have to halt the process before you can recover all the items. So what we see here is that traditional sketches are somewhat inflexible, and there is a design capacity for each symbol. It's roughly half of the size of the sketch, half as many as symbols. And this capacity is fixed when the sketches are constructed. And meanwhile, because in this algorithm, Alice and Bob don't actually know the number of symmetric difference that they want to recover. So they can only guess a capacity that they want to optimize for. And if it turns out that the actual number of differences is too small compared to the capacity, then you waste communication, because recall that all those symbols are sent during the process, regardless of how many items you recover at the end. Or if the actual difference is larger than the capacity, then you cannot decode, right? And so sometimes people using these kind of sketches resort to online estimation protocols, but these estimates are fuzzy at best, and sometimes they also add much latency to the critical path, or sometimes they cause a lot of communication to begin with. So this is the issue with traditional sketches. You have to pre-know the size of the symmetric difference that you want to reconstruct. Then it can be very efficient, but knowing the size of the symmetric difference itself is a somewhat hard problem.
So
Yeah.
So you don't want to send a sketch that allows you to recover the whole set of A, right? Because this would be worse than just worse than sending just A, right? So you're actually sending a sketch based on what you just said,
a guess
of
expect yes, exactly. Yeah, of course you don't want to send the sketch for your original sets, because it's worse than sending the original sets. So usually people first run some online estimation and estimate the size of the symmetric difference, and then they parameterize the sketch generously. So you leave some margin in case there's an error in the estimate, and then you exchange the sketches.
So usually the sets are very large compared to.
Correct. Yeah. Like memory pools, in which case I think each round of synchronization will only send maybe 1% of new items. Okay, so the hope here is that it'd be great if there was a so-called a universal sketch. And what is a universal sketch? And a universal sketch, by definition, it can handle an infinite number of different items, right? And it has an infinite capacity. So it's infinitely long, but on the other hand, it would be great if each prefix of this infinitely long sketch is also a valid sketch that allows you to decode and reconcile a correspondingly, basically a proportional number of items, right? So for example, here, if the original or this universal sketch is infinitely long, it has infinite number of symbols, but each prefix of length m is also a valid sketch, and this prefix will have a capacity that is on the order that is linear to its length m. So that would be very useful, because the way we can use this sketch is that Alice and Bob, they don't really know the size of the symmetric difference, right? So Alice and Bob can now start generating the first symbol out of their infinitely long universal sketch. And Alice will send one symbol to Bob, and Bob will perform a local linear combination to get the first symbol of this universal sketch of the symmetric difference. So Bob has collected one symbol, probably not enough. Bob can, and they can repeat the process, and Bob will collect more and more symbols, and the capacity of this collected prefix will increase, and at some point, this prefix will be long enough for decoding, and Bob has recovered the symmetric difference. So I'll just repeat the process. Alice will incrementally send symbols out of this infinitely long universal sketch to Bob, and Bob will, of course, locally do the linear combination to get symbols from the sketch of the symmetric difference, right? And they don't really know the actual number of symbols or items they want to reconcile, but because they can do it incrementally, and because as you increase the length of a prefix, the capacity increases correspondingly. And of course, all the symbols that you sent previously are not wasted, right? You just accumulate more and more symbols out of this prefix. And at some point,
Do you mind if I just go into the call?
Sorry to interrupt. Yeah, and because you don't really waste any prior transmission because you just accumulate a longer and longer prefix, and at some point, the prefix is long enough for you to decode.
How do they know when to stop? The only assured way to stop is when Alice knows she sent enough symbols to fully recover her set, no?
Good point. So the goal of synchronization is for one end, in this case Bob, to reconstruct the symmetric difference, and Bob can then send back the part that Alice misses back to Alice. So yeah.
Stopping, like when do they stop?
Good point. So because Bob, okay, so it's kind of baked into this protocol, but I'll just give you like an overall idea, which is basically Alice will send. This is one of the solution is that Alice can send a commitment to her set or like a hash of her set to Bob, and Bob, after decoding a few items, right, Bob will just keep an kind of an patched version of his set that will gradually go towards Alice's version, right? The moment Bob decodes an item, Bob applies the item depending on whether it's a surplus or a kind of a missing item on his set, and Bob's set will eventually be the same as Alice's set.
So,
and Bob can compare the hash.
So that's what I said, right? They can only stop when Alice has sent enough symbols to cover her set, no? Do you mean because of the things Bob has locally?
Yes, correct.
But then Bob has to always try subsets of whatever he has locally that's not there.
It's a bit different. So Bob will start with set B, right? And this protocol, when it should finish, Bob will also locally have the symmetric difference.
So you mean that B is a subset of A?
Not necessarily. There can be items that are exclusive to Bob initially, and there can be items that are exclusive to Alice initially.
So it's not one directional, it's bidirectional?
It's the protocol, the communication is unidirectional, but Bob will know, oh, I see. I think I didn't mention an important part. So when Bob decodes, you not only know the symmetric difference, but you also know if the item is exclusive to you or the other end.
So you can only know if something is exclusive to you once you receive enough symbols that cover A.
No.
Otherwise,
once you cover,
you have to try subsets of whatever you think may be exclusive to you, right? You have to try all the subsets. Otherwise, you wouldn't be able to get the same commitment.
So the thing is that this protocol will give you the symmetric difference already, and the symmetric difference includes both the items that are exclusive to you and the items that are exclusive to Alice.
You would take the commitment of B minus A triangle B, and that should be the same as A.
But you don't know, that's not, like the things that are exclusive to Bob, right? You don't know them before you finish.
Correct. You don't know them before you finish.
When you finish, you have this. I mean,
if it's unidirectional, right?
No, you have the symmetric difference.
If it's unidirectional, then how does Alice know when to stop? If you compare commitments, then Bob, until you don't have Alice's full set, Bob would have to take whatever is not in the set already, right? And try to put it and then compute the hash.
So here Bob literally knows from just decoding this sketch which items are the surplus locally. Bob will get that information. Bob doesn't need to guess which item to take
But
away from his set.
that's After it's finished, right? Let's say 0,
Mhm.
right? 0 covers just a single item.
Okay.
Right? Right now, Bob looks at the difference
Mhm.
and all the other items Bob set
Mhm.
may be exclusive to Bob.
So
Correct.
I think the question is like, how do they know once you submit, like, do they know they failed the inspection?
Oh, yes. So if you look at the decoding process.
Thank you so much, Joyce. Sorry to interrupt.
If you look at the decoding process, so this is a successful decoding process, right? And Bob locally sees the mapping, right? Bob sees all those items that are in solid colors popping up locally, right? And Bob also sees the counter in the symbols he cached locally, right? And so Bob knows that decoding might have ended when Bob sees an array of clear symbols with counter equal to 0, with each counter equal to 0. And this is, I used the word might because there might be another symbol here, maybe number 7, that is mapped to only yet another like a new item that is not shown in graph like G, right? So basically, there's always the chance that you get in the next iteration, you get another symbol that maps to an item that you have not even decoded before locally. So basically, having a clear array of symbols does not necessarily mean that you have recovered the symmetric difference or you have recovered all the items in the sketch, but it's an indication, right? And on the other hand, if Bob locally sees something like this, where symbols number 0 and 1 have counters that are not equal to 0, then Bob knows that the decoding cannot have finished, right? So this is the way Bob can tell if he should like try locally.
So it is bidirectional because, like, according to what you described, Bob has to tell Alice, listen, it's not it's not 0 yet.
Yeah, it is bidirectional distance.
So
It's-
if it's bidirectional, then it means that it's always twice, right? The communication complexity is always twice whatever is sent. And if you, in any case, need to get something that's twice as big as the set, then now it's 4 times, right?
What is the size of
The-
the symmetric difference?
Yeah, by set you meant the symmetric difference, right? Not the original sets.
Oh.
Yeah,
So 4 times the size of the
4 times. I would say 2 times
2
because
because of what you've shown, and twice 2, right? Because Bob has to tell Alice in his worst case.
no. So
Bob has to tell Alice.
Never mind.
Bob has to tell. Yeah. So okay. So suppose that Bob's set is suppose that Alice's set is a subset of Bob's set, right?
That's okay. You can just.
Yeah, I think the number is 2, not 4. Yeah, and Alice can stream those symbols instead of requesting an ACK or a non-ACK from Bob in every iteration. So I think that's what reduces the number of rounds of communication. Yeah.
So you said like previously, even in the successful case, Alice may continue to send symbols to Bob.
Correct.
So how does Alice know how those Bob might stop?
So the protocol should be that Bob will tell Alice when he has reconstructed locally the same set as the one Alice committed to, and
So
yeah.
Bob can compute the
Yeah, Bob needs to send a single bit ACK. Yeah. Okay, so the end result is that if you optimize this mapping well, you can actually construct such an universal sketch, and the communication, this coefficient in front of communication cost is 1.35 to 1.58, depending on the size of symmetric difference that you want to reconcile. And the computation cost is, of course, it has to be linear to their sets, because you have to construct originally the sketch for your set, right? Your original set, not the symmetric difference. And for decoding, the computation cost is not, again, It's not linear to the set of the size anymore because it only pertains to
I also have a
the symmetric difference.
question.
Yep.
So for the previous streaming, is it like stream one by one? It's like 1, 2, 4, 8. This kind of stuff.
It's one by one. Yeah, each symbol is number, and you have to take a prefix. Okay, so how do we design a universal sketch, right? And the design space again here is the mapping between, it's the rule that maps an item to this infinitely long symbol space, right? And yeah, if we can have a function that maps any, say, bit string to a subset of natural numbers, then we have the mapping rule. So we just need to design this this function. So the design space is the mapping rule, and the key constraint here is that we want this decoding process to be successful without using too many symbols, right? In particular, we want to use a linear a number of symbols that's linear to the size of the set. And then if we achieve that, then we are very close to be communicationally efficient. So yeah, this is the key question. And we call that, we want this decoding process to be successful. So this problem seems very abstracted, right? There are so many functions that maps bit strings to subsets of natural numbers. So how should I approach it? And we can try to constrain our design space by considering what kind of statistical properties we need so that we can decode with just a few symbols. And for example, let's try to consider the probability where an item is mapped to the ith number, the ith symbol, right? And we call this function, we call this probability rho I. And given any function rho I, we can analyze the resulting random graph from a set of items to a set of symbols, and we can analyze if it can decode with very high probability. So the theorem we prove in the paper is that, suppose that, so let the notation be that it takes m symbols to decode d items. Then the theorem tells us that when that this number of symbols, or the communication cost, divided by the size of the symmetric difference, or this relative overhead m over d, goes to infinite, which is a very bad case because it tells you that it's very inefficient. If either rho I, this mapping probability of an item being mapped to the ith symbol, is not on the order of 1 over I. So it's approximately, right? You have a small wiggle room epsilon here, but basically it rules out any function that is not on the order of 1 over I based on the two theorem, based on the two lemmas. So to give it a visual, to kind of to justify it visually, right? So if rho I decreases too slowly, which means that as you have more symbols, as you go into like a larger index of the symbols, if this mapping probability does not decrease too slowly, then you can kind of visualize that the resulting random graph will be very dense, because even at this point, at the far end, each item still has a significant chance of being mapped to it, right? So the resulting graph is very dense, and the actual converse we use in the proof is that actually, if rho I is not on the order, if rho I is larger than the order of 1 over I, then you don't even have a pure symbol or a degree 1 or a singleton symbol to begin with. It's not even that you'll stop, you'll pause in the middle. You don't even have a singleton symbol at the very beginning. Or if rho I decreases too fast, then the resulting graph will be too sparse, and there will not be enough non-empty symbols, because recall that we're talking about a linear system here, right? And so for example, a dot here, no one is mapped to it, and it's basically an empty function. It's just an equal sign, right? It's not even part of the linear system. So if your mapping function decreases too fast, then the resulting linear system will be yeah, we will not have enough equations to bound the items. So this is impossible for decode. And when this mapping probability is on the order of 1 over I, then it's the perfect balance. You don't have too many like wasted, for example here, wasted empty symbols, and you don't have too dense of a graph at the very beginning, so that you cannot start decoding. Yep.
Why does the difficulty?
Yeah.
Why does the symbols on the left hand side choose so dense?
Yeah, it's by design, right? So this row I decreases with the index of symbol. So so I think the visualization is correct based on this function, but the reason we designed it in this way is because when I think first you definitely need the first symbol to be mapped. At least you need one symbol to be mapped to every item, right? Because if it turns out that you only have one item to reconcile, then you do need the first symbol or the first few symbols to be able to recover that single missing item. So that's kind of yeah, like an edge case that motivates this design. Yeah, but we have only talked about necessary conditions, right? We said that if it's this case, then it does not do. If this is the case, then does not do. But how do we prove that actually this works from like a theoretical standpoint? So again, I mentioned that sketches are very similar, especially the decoding process is very similar to the decoding process for LDPC codes, and we can borrow techniques from coding theory. And you can actually prove in theory that if this rho I function, that's suppose that the rho I function takes a shape of 1 over 1 plus alpha times I, where alpha is just a constant coefficient that lets you like play with different rho I instantiations. So if rho I takes this shape and let eta star to be the overhead, which is m over d, right? The number of symbols divided by the number of items. Then we can prove our theorem, which says that when d, the size of a symmetric difference that you want to recover, goes to infinite, then this overhead takes this shape, right? And we can plot this this function, and it looks like this. So basically, the parameter alpha is the parameter that you can play with in this rho I 1 over 1 plus alpha I shape, and the overhead is the average, on average, the number of symbols you have to transmit per recovered item in the symmetric difference when the number of the symmetric difference goes to infinite. And at the end, we took this alpha, which actually is kind of for a practical purpose because it's easier to implement the function, especially the random process, if alpha is chosen to be equal to 0.5. And the resulting eta star is 1.35, which is achieved when d is sufficiently large. And by sufficiently large, I mean, yeah, even when the size of the symmetric difference is maybe 100 items, the red cross, the actual realized communication cost is about here, so it's actually it's kind of already converged. And you can run more simulations. So 1.35 again is the result given by theory, and the dots are Monte Carlo simulations, and it's yeah, it shows that it converges quickly. And this theorem also tells you the decoding process, right? As you receive more and more coded symbols, you can recover more items from the symmetric difference. So what we see here is like a waterfall process where you gradually recover maybe a few items. For example, at this point, maybe you recover 40% of the items in the symmetric difference when you are very close, but short of this 1.35 decoding communication overhead. And then you receive a few more symbols, and suddenly the fraction of decoded symbols jumps to 1. So this is a very classic behavior in decoding these codes based on random graphs. And there's one small thing, which is how do you implement this mapping rule efficiently? So I think I will skip it because it's just a very small, like, I think it's just an arithmetic trick. So basically, it turns out that you can realize, you can basically take any set of items, you can realize, you can compute the ith symbol from based on the source set of items using very low communication cost. So yeah, computation cost. Sorry, yeah, I'll show some numbers afterwards. And a quick recap: this is how it works. And the reason we call it rateless reconciliation is really because the idea of rateless codes, where yeah, basically it's an idea in error correcting codes that says it'd be great if you can design a code, error correcting code, that is infinitely long, but each prefix is also useful for a certain number of actual errors that you encounter, so that you can be adaptive to the actual error rate. And plus is that the symbol stream from this data structure is universal. So for example, Alice can reconcile with multiple peers with just the same set of symbols. And the symbols are efficiently updatable, again, because this arithmetic trick, if you later want to add yet another item to your original set, then you only need to make updates to O on the order of log m symbols. You just patch them to the linear combination. And we did an implementation. Surprisingly, it only took 400 lines of Go, and we didn't even use any third-party libraries, just from the standard library. And later, someone took the algorithm and implemented it in Rust and C++. So this experiment will focus on the micro benchmarks with other set reconciliation schemes, and also as case study when we use them to reconcile, to heal the Ethereum account states. So I think I will quickly go through the micro benchmarks, which basically says that the communication overhead converges quickly, and it's better than other solutions based on random graphs that required you to estimate the size of the symmetric difference. It is worse than what we call ping sketch. Ping sketch is okay. So our solution is based on random graphs, and there's another class of codes which uses linear systems, which uses more dense linear systems, which is denser linear systems, right? And yeah, it's called ping sketch, and the corresponding code is basically Reed-Solomon codes in error correcting, in the world of error correcting codes. Yeah, the kind of the difference here is very similar to like LDPC codes versus Reed-Solomon codes in error correcting. LDPC codes is very easy to compute, but it's not perfectly communicationally efficient. While here, yeah, ping sketch is perfectly communicationally efficient because it sits at 1 exactly sharp throughout the regime, but as I will show here, it's not very computationally efficient. Yeah, so here the comparison is for encoding sketches, and as the size of the set differences increases, the encoding throughput plateaus for ping sketch, which is a variant of Reed-Solomon codes, while for our solution, it just increases with the set difference.
Well, how to read this?
Yeah, it's yeah, I took it from the paper. So x-axis is the set difference for which you encode, right? It's supposed that you are ultimately you are encoding for a set difference of say 1,000 items, and then you can compute if I'm going to encode for if it ends up that I encoded for a set difference of 1,000 items. I use the word ends up because Alice does not initially know how large of a set difference she should prepare for, but she will just incrementally encode more and more symbols. So she can then take a look at how much work she has done after Bob has reconciled, right? So suppose that we pick this point, and I think the solid curves are for the left, the Y1 axis, the Y1 axle, and this tells you the encoding throughput. In other words, to encode the number of items in Alice's original set that can be encoded per second, and on the Y2 axis is the time it takes for Alice to encode over her entire set for, say, this number of items. And we also did a comparison with computing SHA-256 of each of the items, and turns out that the throughput, so this is the time, the red curve, to compute SHA-256 of each of the items in Alice's original set, and turns out that over the regime, across the regime, the time it takes to compute the sketch, which we call Rateless IBLT, is quite similar to computing the raw SHA-256 hashes. And finally, a quick case study. In Geth, the Go Ethereum client, there's a step called a state heal that kind of fixes corrupted databases by reconciling your database with your peer's database. And currently, it uses it walks the Merkle-Patricia trie with your peer in sync. And because the Merkle-Patricia has not grown to be very large, it takes weeks in some cases, especially with high network latency, for you to finish this process. And you can see all those complaints on GitHub. I took these screenshots when I was writing the paper, I think 1.5 years ago. I'm sure there are more complaints popping up. Yeah, and you can send the entire snapshot, which basically means that you redo the snap sync, or you can download the log, basically the new blocks, and you just locally recompute the transactions. But these all require Bob to have a consistent database. But what if Bob's, say, disk is corrupted, right? Some of the keys are corrupted, and Bob no longer has a consistent snapshot of state as of, say, some block height, right? It's very problematic because you cannot re-execute any transaction based on an inconsistent piece of state. Yep. So yes, you can use set reconciliation, and this is the experimental setup. 0.5 terabyte of RAM, kind of ancient server CPU on data center grade SSD running on FreeBSD 14.0, and yeah, we did the implementation. The workload is to reconcile, I think, 5 days worth of Ethereum blocks of difference, right? And if you vary the staleness, which is so the scenario here is that Bob goes offline at some time t, and then Bob recovers after this number of hours, and then Bob reconciles with Alice, who has always a fresh, up-to-date state snapshot. And you can see here that it's a big difference between using reconciliation and walking the Merkle tree. Yeah, it's just a zoomed in version. And I think the key difference here is the latency. And it's really because if you use reconciliation, you only need one round trip. I think Aviv may disagree because, yeah, technically Alice needs to send multiple symbols before Bob can say, yes, I have finished, but it's just one round trip, right? In those so-called fat pipes, which will have very high bandwidth in the network, but also very long latency, it's especially problematic because if you go back and forth all the time, like you do in like walking the Merkle tree, then you cannot really make fully use of your network bandwidth. It's always like I send you a little bit of data to kind of open the 2 children and multiple children in the case of Merkle-Patricia trie, and then it takes very little data, right? So most of the time is taken by the speed of light propagation delay, and you can see here that you have a very small tick here to open the initial to open the root, to open the children of the root. And you have a few ticks here, and only here can you find the bulk of the differences, and you really start to use the bandwidth. But here in Rateless IBLT, you just make one spike. Alice just Alice just starts sending, pumping her symbols to Bob at maximum line rate, and Bob acknowledges, and the protocol finishes. And here the line rate is 20 megabits per second in our experiment. Yep. So yeah, here is the conclusion. So we talked about an primitive which I found very interesting and underappreciated in distributed system engineering, which is called set reconciliation. It allows you to reconcile two sets of data with near optimal communication and computation complexity. So the novel stuff in this work is that you no longer need to by importing ideas from coding theory, you no longer need to pre-know the size of the difference you are reconciling. There's no parameter in this protocol, yeah, it's very easy to implement, and you can actually get to, I think, hundreds of megabits per second in terms of reconciliation throughput when you are running it over the networks. Yep, that's it.
Can you go over maybe the protocol slide again now that we know how the code works?
I think
yeah. Discuss back and forth support.
Yeah.
Sorry, before that. Before you introduce. Yeah, here. You just describe again how Alice, what does Alice and Bob do?
Okay. This one, right?
Yeah.
Okay, so Alice computes a sketch for her set, and Bob also computes a sketch of his set locally. So this is all done locally, right? Computing a sketch only requires knowledge of the set that you compute for.
Okay, Alice first estimate a V and
yeah, in traditional protocols, yes. So they first, yeah.
Your protocol.
Okay, so in my protocol, I should go here. Let me see if I can. Okay, yeah, I think this one, yeah. Okay, so Alice computes the first symbol of the sketch for her set.
Okay.
And Bob computes the first symbol of the sketch of his set.
Okay.
It's all done locally. And then Alice sends this symbol to Bob. And Bob will do a local linear combination. And the result, because the two sketches they are still linear sketches, so the result is the first symbol of the linear combination of the sketches, which is the sketch of A delta B, the symmetric difference. This is correct, right? We're on the same page. Okay, so, and then Alice can just repeat the process so that Bob will accumulate more and more symbols with higher and higher index in the sketch of their linear combination.
Bob will try to decode this.
Yeah, every time Bob receives an extra symbol, Bob tries to decode. And based on some criteria, Bob can tell if decode has definitely not finished or it might have finished. And in the latter case, for example, here, Bob sees these items, and some of these items are local to Bob. And if they appear in the decoded set, then it must be the case that, for example, this blue item, right? If Bob sees the blue item in the decoded set, but also in his own set, then it must be that it's an item exclusive to Bob. Then Bob subtracts the item from his set. But for the other two items, for example, maybe they are not present in Bob's set, then Bob adds them to his set. And then Bob, after doing this patchwork, Bob compares the hash of his set after the patching with a commitment sent by Alice with the first symbol. And if they match, then Bob knows that he has reconstructed Alice set, and also he knows which items were exclusive to him and which items were exclusive to Alice, and then Bob can send, say, this blue item to Alice so that Alice also gets the missing item. But this is optional. Yeah.
And the 1.35 is the number of symbols sent over the number of cement.
That's the symmetric. Yes. Mhm.
Oh, I see.
Yeah, and actually we later did some optimization, and you can bring this number down to 1.08 or something by using more fancy random graph construction techniques.
Because the part I didn't get is that the decoding is for the symbols for the symmetric difference.
Yeah, that's the key that makes this protocol and also the previous protocol that requires estimation to be only dependent on the size of the symmetric difference. Yeah. Cool. Are there any questions?
So what is, or I don't know if this question, but what is the overhead you pay for this like iterative property on the coding? And or is there an overhead you pay like with respect to using the previous scheme and let's say if you got the prediction right before and you just predict and then
Oh yeah, good point. There is no overhead because yeah, in terms of the number of like additions, subtractions, linear combination you do, there's no overhead between you do a batch, if you decode like a batch of symbols at a time versus you do it iteratively every time you receive a new symbol, you do it incrementally because the actual decoding process itself is iterative.
right?
Yeah.
But now there's this property that like maybe one symbol allows you to decode like one element, like every element, or no, or maybe I'm
the communication cost is, if you're talking about the communication cost, then yeah, it's actually lower than the batched version of the code. I think it's because of a lack of effort in optimizing the batched version of the code, but the best you can do is one, right? For the size of the symmetric difference to be the same as the number of symbols you require to decode them. And for us, we got to 1.08, and for this batched codes, they got 2, but I think yeah, it's actually easier to improve those batched codes, and they can actually be very close to 2. Be very close to 1. Yeah, if you really try very hard, like playing with a lot of random graphs.
And do you have to balance the probability of not being able to decode something, or it's just
no, because
settled by your 1 over?
Yeah, eventually, yeah, it's solved by this row function. So there's no parameter. Eventually, as you send more symbols, you're bound to decode this. Like probably goes to 1. Yeah. Cool. Yeah, I think I'll wrap it up. And thanks a lot.